also privileged to have with us our respected principal, Honorable Dr. O.S. Deshmukh sir, the dynamic leadership of Indian Association of Physics Teachers, Professor P.K. Ahuja sir, who is with us on online mode. We have with us Professor Rekha Ghurpade ma'am and all distinguished guests over here. So I again welcome you all. Ladies and gentlemen, we are delighted to have our honorable guest here with us today. Let's move forward to mark the auspicious beginning of this guest lecture. I request all the dignitaries to pay their respect by offering floral tributes to the portraits of the great scholar of education, Dr. Panjabrao Elias Bhausar Deshmukh and Rashtrasanta Tukadoji Maharaj. The first agriculture minister of India, Dr. Panjabrao Elias Bhausar Deshmukh, and the great saint Rashtrasanta Tukadoji Maharaj. Let's extend a warm welcome to our guest of honor. I would like to request Honorable Principal Dr. O.S. Deshmukh sir to welcome Honorable Dr. Ashish Mahaval sir with a bouquet of flowers. I would like to request Honorable Head of the Department and President of Indian Association of Physics Teachers, SRC 080, Vidarbha, Professor Shamkant Anwale sir, to welcome our Honorable Principal, Dr. O.M. Deshmukh. Welcome, sir. Now I would like to request Dr. Sugandha Chanda ma'am to welcome Honorable Professor Shamkant Anwale sir. On behalf of Physics Society, Science College Congress Center Nagpur and Indian Association of Physics Teachers, Sub-Regional Council 080, I welcome you all for this particular guest lecture. To give us a formal introduction to today's event, I invite the Honorable Professor S.W. Anwale sir, Head of the Department of Physics Department and President of ISPSR 080.
Thank you, Jadhav sir. I take this opportunity to welcome one and all here. I remember the great Maratha warrior Chhatrapati Shivaji Maharaj, and I pay humble tribute to Dr. Panjabrao Deshmukh, who started educational society in the name of Shivaji. Our guest speaker and a student, the wonderful combination we have. Dr. Ashish Mahaval from Caltech, California Institute of Technology. Our principal, Dr. O.S. Deshmukh. I recognize the presence of our esteemed teacher, Professor V.P. Sapre sir. Welcome you, sir. Sari, Arukar, all faculty members of our department, students, and I also recognize the presence of teachers who are from IIPT, Professor P.K. Ahuja sir, Central President of IIPT, and Rekha Ghurpade Madam, Secretary of Central IIT. This is a wonderful occasion on which a senior professor like Sir Sapre, Professor Kamal Singh is on the way to reaching to this hall any time. They will be sitting in the audience and their student, Ashish Mahabar, will be delivering lecture. And I believe that this is a very rare and wonderful occasion since that Dr. Mahabar has reached to a very good position and has done wonderful work in his path. I remember a nurse, sir. A teacher is guiding student and a father is guiding his son. That sort of combination we are having. I often recite this poem in the student induction program for newly inducted students. हम लोग अपने माता पिता का हाथ उंगली पकड़कर स्कूल में जाते हैं और एक टाइम आता है कि उनका हाथ छोड़ना पड़ता है, वो भी एक रस्म है. So a fatherly teacher is saying something to his student and reciting the words of Iqbal Asher. मेरे बेटो मेरी उंगली ना पकड़ो, मेरी ऐनक से दुनिया को ना देखो, मेरे नक्शे कदम पे खाक डालो, मेरे रास्तों से रास्ता मत निकालो, मोहब्बत की नई तकसीर निकालो, बुलंदी की नई ताबीर लिखो, मेरी ये ख्वाहिश है तुम ये कर दिखाओ, चलो रफ्तार कुछ और बढ़ाओ, तुमसे पिछड़ने का बहाना चाहता हूँ, इसी में जीत पोशीदा है मेरी, मैं तुमसे हार जाना चाहता. A teacher wants his student to excel, and that is the greatness of teacher. And this is the occasion today to our students and faculty members also. I want to mention that Dr. Ashish has qualified his BSc from Shivaji Science College, Nagpur in 1990. And then he did MSc from Nagpur University, RTM Nagpur University. Nowadays it is called RTM Nagpur University, wherein he was student of Sapre sir and Kamal Singh Madam. So I wanted to tell this to students because students are in position to relate where they can go, how they can develop their career. With these words, I conclude my saying. I would appreciate Dr. Ashish sir's efforts to come back to our college and enlighten our students and faculty members. Thank you.
It's been a great moment for all of us. Today we have some eminent professors and teachers. We have with us Professor Sapre sir over here, Professor Khasare sir, Professor Darokar sir. I would like to welcome you all from this Department of Physics and Indian Association of Physics Teachers Sub-Regional Council 080. Now, let us hear about our eminent guest speaker from one of our brilliant students, Miss Aishwarya Megawde, who is the president of Physics Society and a BSc final year student. So I call upon to Aishwarya here to introduce our guest speaker.
Good afternoon, everyone. I am Aishwarya Megawde, student of BSc final year and the president of Physics Society. It is my distinct honor to introduce a truly remarkable individual and an alumnus of our college, Dr. Ashish Mahabar sir, a visionary and an expert in his field. Dr. Mahavar sir is widely recognized for his groundbreaking contributions to astronomy and astrophysics, where his innovative approach and unwavering dedication have left a significant impact. Sir is a distinguished astronomer and data scientist, holding a dual role at the prestigious California Institute of Technology in Pasadena, California. Dr. Mahavar sir served as an astronomer in the division of physics, mathematics, and astronomy, as well as a lead computational and data scientist, Center for Data-Driven Discovery. He also serves as an adjunct faculty member at the Inter-University Center for Astronomy and Astrophysics in Pune, where he earned his PhD. Dr. Mahabar sir's research interests include large sky surveys, machine learning, and classification, with application extending data fields such as medicine. He leads the machine learning team for the Zwicky Transient Facility, that is ZTF, a revolutionary large sky survey that continuously monitors the northern sky, capturing data every few nights. His work is transient. Astronomy significantly advances our ability to identify and classify astronomical events in real time. Beyond his stellar contribution to astronomy, Dr. Mahabar sir actively collaborates with the data science group at Jet Propulsion Laboratory and is a prominent member of Early Detection Research Network, that is EDRN, where he contributes to cancer research. He is also part of Consortium for Molecular and Cellular Characterization of Screen-Detected Lesions, applying machine learning technique to early-stage disease detection. By merging his expertise in data science with cutting-edge application in medicine, Dr. Mahabar sir is driving advancement in both physical as well as biological sciences. With his vast experience and passion for making a difference, Dr. Mahabar sir has established himself as a leader who not only excels professionally, but also monitors and inspires others to push the boundaries of innovation. With his work exemplifies a steadfast commitment to improving science and society, touching countless lives along the way. Today, we are privileged to have Dr. Ashish Mahabar sir with us. His insights, expertise, and unique perspective will surely inspire us, and we will surely enlighten. Please join me in welcoming Dr. Ashish Mahabar sir to share his valuable words.
How do I advance slides? Do I tell someone to do that? I'll let you know. Okay. So thank you again for the warm welcome. It's really good to be back back in Nagpur as well as Shivaji Science College, where I spent 2 very fun years. I'm sure the students who are here, students right now, are also having fun. Today, what I'm going to talk about is utilizing rich astronomy archives. And as Mani sir said in his poem about Nazma, that how students can exceed their professors. These archives, astronomy archives, which have a lot of data, which is available to everybody, will allow all students to exceed everyone if they have that in their minds to do that. Because what has happened in the last several years is that the data are there, the tools are there, the internet is there. All you need is your will and the knowledge to find out where the data are. It's easy to pull them. You don't have to write new code. Most of the code is there. You can just put things together and you can do interesting fundamentals. As was mentioned earlier, I'm at Caltech, California Institute of Technology in Pasadena. I'm the Deputy Director for the Center for Data-Driven Discovery at Caltech, and also lead the machine learning for Zwicky Transient Facility, about which I'll be telling you soon enough. So this is the broad outline of my talk because our audience is quite broad as well here and online. I'll give a very broad overview of how astronomy is done today. In particular, how astronomy used to be done and how it has been changing. Sorry, I should have told you. We are on the next slide. The way astronomy is changing, focused observations, observations to surveys. Long back, what used to happen is that the field of view of the instruments used to be small. You go to telescopes and take specific parts of the sky. But since then, technology has changed so much that we can take something like slow movies of the sky. So we have large surveys where the camera can take a very large field of view, and then we can keep on taking successive images of different parts of the sky. So we can keep coming back to the same part of the sky again and again. That allows us to see changes in the sky. Earlier, you could do detections, you could try to figure out what is in that part of the sky. But now you can ask what was there before, what is there now, how are the things changing? So those kinds of things can be done. The way the world is changing is that we have got fast wonderful computing. There are computers and large to write most of the code yourself. And large cameras in astronomy. Again, the camera that I used before when I started my work was really tiny, covering a small part of the field, but there have been much bigger cameras now using CCD. And data availability archives, that's the main part of this talk. I'll be going into more details about that. So I won't be spending equal amount of time on this, but through the broad introduction, then whatever questions you later have, we can come back to that and have discussion related. What this allows you to do because of these large archives is that most of the astronomy teams go after low-hanging fruit, easy problems to solve, something that can be solved quickly, because the data are so much that much more can be done. And people who have access to computers, who have access to these data, forming teams can go after much more intricate problems, especially if you have a good grounding in statistics. That's not required for everything, but if you have that, then you can go into even more details. And machine learning and AI can be used extensively now. And finally, I'll tell about ZARC again that we have developed for outreach that puts astronomy in the hands of everybody now. For instance, many of you may have heard, maybe you should tell me by raising your hands. How many of you have heard of Pokemon Go? So there was a game where you could go around and catch Pokemon. So we have developed the same game for astronomy using real data. So you can point your phone to the sky, look for transients that we have detected. We put in new transients every night, and you can catch those transients, climb leaderboards, compete with each other, and learn about astronomy in the process through gamification. So we'll see a little bit about that. So what does astronomy cover? Right, next slide. So what does astronomy cover? Obviously, the solar system it includes our sun, it includes the planets. So for instance, now we have gone to Mars, we have gone to one of the asteroids, and we are trying to explore more areas, moons of Jupiter and moons of Saturn. So a lot of research is happening there. Asteroids. One day we may need to mine asteroids, maybe pull an asteroid close to us so that we can get minerals from there, and so on.
Thank you.
Then going beyond the solar system, there are all kinds of stars. Our sun is a specific star, but then within our galaxy, there are 100 billion stars. And there are all kinds of stars, young, old, binary stars, or stars and binaries, stars that are red giants, stars that are white dwarfs, and so on. So there are a plethora of studies that can be done there, supernovae stars that explode. Many of them we see in other galaxies, because in our galaxy also there have been some, of course, and thankfully none very close to us. Otherwise, life on Earth may end if there is a supernova very close to Earth. Then there are different kinds of galaxies that we can study: spiral galaxies, elliptical galaxies. There are clusters of galaxies. So all that comes in astronomy. And what surveys enable you to do is that surveys look at everything. So you cover the entire northern sky, and there are stars, and there are galaxies, and there are asteroids. So you can get data for them, and then whoever wants to study whichever part of that can be studied. And in recent years, there has been a lot of study of exoplanets, looking for planets around other stars. And we have several thousand examples of that now. So all those data are stored for free in archives, which can be downloaded by anyone. And then cosmology is, of course, the overarching study of understanding, say, the evolution of the universe or the composition of the universe, how much dark matter, how much dark energy, how fast it is expanding, etc. And then the way we study this is in using optical wavelengths, using radio wavelengths, X-ray, gamma rays, the whole electromagnetic spectrum. But besides photons, besides electromagnetic spectrum, in recent years, there have been new ways to study the cosmos as well. We can study them with gravitational waves now. So there are two large gravitational wave detectors in the US. There is one in Italy, and there is one happening in India very soon. So in Maharashtra, in fact, near Hingoli, so a gravitational wave detector. So India will be squarely on the map in terms of that instrument. In terms of scientists doing gravitational wave observations or studies for that, India has been in the forefront for a long time. So that is already there. But we also have this. We have also been doing observations using neutrinos. There's the ice cube experiment where we can detect neutrinos coming from other parts of the universe and try to figure out where they are coming from, what kinds of objects they are associated with. And there's huge scope in terms of instrumentation and development of methodology. Next slide, please. So again, brief look at how changes in astronomy have been happening. So on the top right, you see an image where you see two images of the same part of the sky. You can figure that out by the same set of stars there. But as you can see from the dates below, one says 1990 and the other says 1992. So these were taken 2 years apart. These are in fact small parts of large photographic plates. So this is before charge coupled devices came into existence or extensive use. All of you likely have smartphones. They are fantastic cameras. You hardly ever see anyone using cameras with rolls these days. That was the norm. Even in astronomy, exactly the same happened. Until about 30, 40 years ago, there used to be photographic plates that would be at the back of telescopes, which would collect the photons, and then you would go into a lab, develop those, and then you would do the observation. So when I went to Caltech 25 years ago, I was working on what is called the digitized Palomar Observatory Sky Survey. The word digitized tells you that the original observations were not digital, they were analog, they were these photographic plates. These are photographic plates roughly of this size. They would cover about 6.5 degree by 6.5 degree of the sky. The moon and the sun, for comparison, are about half a degree. They subtend an angle of half a degree on your eyes. This is 90 degrees, and the moon and the sun are roughly half degree. And the moon and the sun, their physical sizes are very different from each other, of course. The moon is much smaller than the Earth, the sun is much bigger than the Earth, but their angular sizes happen to be same, roughly same, because moon is much closer to us. And that is why we can have total solar eclipse as well as total lunar eclipse. And then these survey plates that we had would roughly cover 200 full moons. Those were that big. And then we needed 1,000 such plates to cover the entire northern sky. And at that time, it took 15 years to cover in 3 different filters the northern sky. So think of 1,000 plates and then 3 filters, so 3,000 plates. So 3,000 plates took 15 years. And the total data over those 15 years was 3 terabytes. And right now with our current survey, we get 3 terabytes every 2 nights. Think of that, 15 years to 2 nights. That's how the scaling has happened between then and now. And of course, the resolution has improved, the depth has improved. So we can see fainter now, we can see better now. And that's how things have changed in many, many ways in all walks of life. And that is where we can use all this data. So at that time, the best storage devices were exabyte drives. Each exabyte drive could hold 1 GB. How much do your phones hold now? How many of you have 128 GB phones? So we had the maximum we could hold was 1 GB on one day. And because it was 3 terabytes, we had 3,000 exabytes to hold the survey data. And now, of course, we have hard disks that are 20 terabytes, 30 terabytes. So photographic plates to charge coupled devices, 1 epoch in 15 years, now 500 epochs in 5 years. We have that many observations. That is why I said now we have something like a slow motion movie of the cosmos. We can keep seeing the same part of the sky. So what took us 15 years to cover the entire northern sky in 3 filters, now in 1 filter we can cover it in 2 to 3 nights. So every 2 to 3 nights we see the same part of the sky, and that is why we can see what is changing there. Which stars are becoming fainter, which are becoming brighter, at what frequency, etc. And that gives us a much better understanding of our galaxy, which was just not possible. And so the magnitude system is logarithmic. Zeroth magnitude is the brightest object that we can see in a good night sky, and fifth magnitude is roughly the faintest. So these five magnitudes are a factor of 100. And then with our survey, we can see up to 20th magnitude. So we can see 1 million times fainter with our survey than what our eye can see. And there are many surveys happening. So we'll see a bit more about that. CRTS was a survey that I was working on earlier. This is the Catalina real-time transient survey. They were looking for asteroids. So they would take 4 images of the same part of the sky 10 minutes apart. The first 3 would be used to see if some object is moving, because all the stars, once you account for the motion of the Earth, would be stationary. But if there is an asteroid, then it would have some proper motion. And between the 3 images taken a few minutes apart, you could see it move a little bit. And then you would fit an equation to it, you would figure out how fast it's moving and predict where it should be in the 4th image and see if it is really there in the 4th image. That way you know that it is indeed there. So then Gaia is another survey that is being done from the sky. We have been looking from the sky that gives very good astrometric accuracy, positional accuracy, much better than from the Earth. Because on Earth, the observations that we get go to the atmosphere, we come out of that. ZTF is the survey that we are doing, the third one that you see here. That's the ZTF one. This is a different projection, but we cover only the northern sky because it is from Paloma, northern latitude, so we cannot see in the much in the south, so that part is not covered. And the black part that you see there is the southern pole, for instance. And Rubin LSST, they had their first flight a few days back. So that survey is starting in Chile. It will be covering the southern hemisphere, and it is a much larger telescope. The ZTF telescope has a diameter of only 1.2 meters, whereas Rubin has a diameter of 8 meters. So it's going to be getting more photons and you can see much deeper. So it will be able to see objects that ZTF cannot see. And so we'll be able to see more details of things, we'll be able to see fainter objects and all those kinds. There are many parameters, and all these surveys are just in the optical line. There are other surveys in infrared and ultraviolet and X-rays and gamma rays, whole plethora. So looking at some specifics like stars, for instance, we think there are stars, but there are stars of various kinds. There is a quote from one of my favorite science fiction books here, from Douglas Adams' Hitchhiker's Guide to the Galaxy. It says, far out in the uncharted backwaters of the unfashionable end of the western spiral arm of the galaxy lies a small, unregarded yellow star. And that's what we are. So next slide, please. So we are on this slide. So this is the quotation that you see below. So far out in the uncharted backwaters of the unfashionable end of the western spiral arm of the galaxy lies a small, unregarded yellow sun. Indeed, our sun is really an ordinary star. It is somewhere in the middle of this Hertzsprung-Russell diagram. And out here are white dwarfs, much smaller bodies. Whereas on the right, there are blue giants, red supergiants, etc. Lots of different things on the right. So very different kinds of stars, and we can tell you all of those. Next slide, please. So let me quickly mention here a few archives of the data that we have, and I can leave a list of these with Professor Angwane. You can collect them later on. And we'll also, you can ask me questions about it later about how to get those. But let me quickly go through some of them. So NASA IPAC has this archive called IRSA, where there is infrared data from missions like WISE, Spitzer, TUMAS, and there are also tools for analysis. So you don't have to invent any of those. Those are there. You can just get those. The Mars survey has data from space telescopes like Hubble, the transiting survey for exoplanets, and Kepler and JWST, etc. These have optical and ultraviolet products. High energy astrophysics data are on GISARD. So again, these include X-ray, gamma ray from Chandrayaan Explore. So these are either satellites or telescopes on Earth. So lots and lots of data. The ESO Science Archive facility has data from VLT, ALMA, LASIA, and many different telescopes. ALMA has a lot of radio data, millimeter, submillimeter. This is used to study dust and gas in our galaxy, how stars form, etc. They're in their infancy. Then the Neuer Lab Data Archive has ground-based data from Gemini, Kepler, etc. NASA Exoplanet Archive has data about various exoplanets. ESA's Gaia Archive has data from Gaia, the very high resolution positional data that I mentioned. Again, there are billions of stars there. Low resolution spectra are available with those. BZA, the CDS service, has thousands of astronomical catalogs across all wavelengths. These also, when people publish papers, and those papers have tables of objects that they have studied, many people in astronomy these days have been making available those data as well. So those data are also available in some of those catalogs. So you can download entire tables and latest Python scripts that are also available. You can analyze those quite easily for things that they may not have thought of, or you can combine different data sets very meaningfully, very easily. So all those tools are also available with these. So ZTF is the survey that I work on, so I'm going to go into some more details about that. And you can see very large numbers here. These are mind-bogglingly large numbers. As I mentioned, ZTF, a single field of view is 36 plus square degrees, 47 square degrees actually, 47 square degrees, roughly 200 full moons. And we cover that and all those 3 times. So the number of objects that we get are really large. So G, R, and I are the 3 filters that we use. So if this is the electromagnetic spectrum, these cover small portions of that. And why we use different portions of the electromagnetic spectrum? Because they tell us about the temperatures of the star, they tell us about the dust content of the stars, etc. And then because each image is so large, the number of objects is very large. And because we have a large number of epochs, several hundred epochs, then all those things multiply with each other. So think of it, billions of stars, several hundred to 1,000 times. That is how these numbers come here. So very large numbers in each of these bands. And then we create different kinds of catalogs. And the URL here shows where you can get the data from. And we have multiple releases. So every few months we provide new release because we are taking more data. So instead of telling you that this is how bright this particular star is, because we have observed it many times, what we provide is a time series of the data. And it is the study of these time series that makes astronomy really interesting, because that's where we understand how things have been changing. So the main drivers, science drivers of CTFR, we look for fast, young, and rare flux transients. So yeah, they're on the right side. We also look for counterparts to gravitational wave sources. I mentioned that earlier. So gravitational waves with the current LIGO detectors, if 2 neutron stars collide or 2 black holes collide, they lead to gravitational waves. And the gravitational wave detectors simply tell us that a gravitational wave event has happened. It is not very directional. So if we get a very large map saying that somewhere in there that has happened, and then it is the optical telescopes that need to go there and look for possible counterparts. So we have been doing that. Low redshift type 1A supernovae for cosmology, because we need to understand using this standard candle. So supernovae of a particular kind burn the brightness that is very specific. But just like candles, if you have a standard candle here and if you take the same standard candle twice distance away, then its brightness that you perceive is 1/4 of that, because the surface of the sphere goes as square. Similarly, the supernovae, because they have fixed maximum brightness, if it happens at twice the distance, you know how faint it would be. And so by looking at the apparent brightness of the supernova that you see, you can tell how far it is. And that is what is used to measure distances of galaxies, and that is what is used to understand the expansion of the universe. So that is what we have been doing it with ZTF as well. And then lots of variable stars, eclipsing binaries, etc. Solar system objects, all kinds of those asteroids. We have orbits for a very large number of asteroids. We find new comets when they are really far off and we see only a speck of them. We can detect them and try to predict how they are going to approach us. And one of the things that we do in the twilight is also look for asteroids that may possibly hit Earth. We don't want that to happen. So creating a better and better catalog of that. Next, please. So this shows the kind of studies that we have been doing with transients. Transients are objects that change in short amount of time. It could be a variable star, it could be eclipsing binary where the change is apparent, not something happening inside the star, but because one star eclipses another, or it could be something like a supernova. So we study them using the time series that I mentioned. It could be extragalactic within the solar system or whatnot. And the tree on the right hand is actually only a subset of the tree. There are so many different types of stars that we try to cover as many as possible. But again, even with our survey, not everything is possible, and that's why we need even bigger surveys later on. Or in the data, there may be more things that with better techniques, you'll be able to use the data yourself to find more of these objects. Next, please. So this is how we release our transients. So as I said, our archives are public. We try to provide the data quickly to everyone. So when we detect new objects, in real time, we publish the information about them, what is the location of the object, what is the brightness, and what we estimate how faint it is going to become related to them. So the three images that you see here are the new image, the reference image, and if you subtract one from the other, what is the difference that you'll see? So static stars, they will subtract out from each other and become flat, whereas if there is an object that has changed, then you'll see something there. And our images are big, so this is not the size of the image, but then we have algorithms looking for these changing objects, and whenever we find something, then we take a cutout around that, and the triplet that we see is something like that. And what you see below is the time series for that, how it has been changing. So the early points were flat, the object was not changing, but suddenly became bright. It's likely to be a supernova then, and then at some point it will go down again. And the game that I mentioned, those are the kinds of things that you can catch and learn more about. So here are some examples about how we convert the time series into something that is more amenable. So time series, because the sky has its own vagaries, sometimes the moon is bright, sometimes the weather is bad. So you cannot say that I can always get observations at this regular interval, and sometimes regular is not best also to look for variability. So from the irregular time series, we need better techniques to make sense of those. And so we develop various things like decision trees, random forest. These are machine learning things for which libraries are available, which you can use to do various things. And we also developed deep learning techniques with that. So what you can do is that you take a time series, take pairs of points, you figure out the delta t and the delta magnitude and convert that into a 2D histogram. So now you can use it with something like deep learning. So how many of you have heard about or used deep learning? If you let me know. So some of you have. Okay. And then so here what you can do is that with these images, you can just like you would have heard of this example where there were engines that were used to train to recognize cats and dogs. So you give a picture of a cat or a dog, and the machine learning algorithm recognizes that. So similarly, for our scalar time series, we can convert them into 2D histograms and then train an algorithm on that to say which is of what kind. So RRI is one kind of star, CV is another kind of star, or supernova is a third kind of star. So we can give many examples of that, and from that, this machine learns as to what kind of object that is. And then when you give it an unknown kind of star, it gives you with a certain confidence what kind of object that is. So next slide, please. So this is where you can see how the different kinds of stars look. And on the left-hand side, at the top, you see light. So that is what a time series in astronomy is called. And then there is the density representation of that. And then you can describe, get the equal area images from that. And then the convolutional neural network is what is trained to identify between these different things. So cats and dogs are no different from these images so long as you have a good training sample. And once you have a good training sample, you can use it to train it to identify these different areas. And then what we do is that one of the focus of my talk, rest of my talk is going to be stellar science because there are many other things we can do, but I don't want to take on just one, so that's what I'm picking. So within the stars, we're using archival data again. The transient part, you find new things and you say that this is what we have found. But with these things, what we do is we find different kinds of objects, and then the main thing to do is that if you try to identify between 10 different things simultaneously, no matter what algorithm you use, it can get confused. It can try to optimize for one, a little bit for the other, a little bit for the third. So what we decided to do is that run a large number of binary classes. So for each class we are interested in, ask whether that object is of this type or that type. And with this hierarchy, we can easily find out for that. So this shows, for instance, how the yellow means high confidence. The object we are looking at right now is an RRI type, which is a pulsating star. So our classifier says the first one is variable or not variable. It says it is variable. The next says it is periodic. The third says it is irregular, not eclipsing. So the yellow high means yes, and yellow below means no for that particular kind. So the first is variable, second is periodic, third is irregular. All these are binary classifiers. And you can see that for the pulsating one, which is 1, 2, 3, something like 10 from the left, and then the 13 from the left, again it is high. So by using these multiple binary classifiers, we know which class it belongs to. And then you can go down this tree for each object, and then you get intimate knowledge of each of these types of objects. And then what we are also interested in is figuring out what are the gaps in our survey. So with these surveys, we can find out there are many objects of this type, many objects of this type, and different teams are interested in specific classes. But what is it that they're missing? So that's what we are trying to understand with this technique called Frigate, where we see that, okay, so think of it in this fashion. This room is 3-dimensional. And if you have 3 parameters, then each axis can be treated as one parameter. And then depending on what values those parameters have for an object, they'll occupy one part here. So one star could be here, one star could be there. But we have 50 different measurements. What that means is that we have got a 50-dimensional space. And there's no way we can make physical sense of that. Even mathematically, it's non-trivial. So we have to first reduce it to a smaller dimensional space, say 5, 6, and within that determine where our different areas are. But then what this frigate allows us to do, tell us is what are the gaps there? What is the area in this large dimensional space where we have no information, or we have objects but we are not even paying attention to them. And that is another area where using the archives, people can explore them much more, go into that area. So look at those. Another thing that has been happening in machine learning and AI are foundational models or foundation models. What these foundation models do is that you can train a model on one set of data, but then you should be able to use it on another set of data without training it anew. Because for instance, if let's say we want to do face recognition, and we did face recognition using examples of people in this room, then this is all of us have Indian physics. So the training algorithm will learn about Indian physics. And then if I took it to say South Africa, or if I took it to Sweden, the algorithm is not going to work very well. It will still work to an extent, but not as well as how it will work here. So what I need to do there is I need to take an additional sample of people from there and do some fine tuning of the algorithm. But what foundation models allow you to do is by taking a large set of different kinds of examples in one go, it trains it in a way so that you can take it from one place to another place. And that's what we want to do with different surveys. I told you about large number of surveys, so you train on one survey and take it on another. And an example is the large language model, ChatGPT. How many of you have used ChatGPT? Or and if you are model, almost all of you, right? So what happens there is that it is a large corpus of language or different corpora of languages. And that is what it is trained on, and it learns the language really well. And then when you ask it to write something, it's really good at that. So that's an example of a foundation model for language. Other foundation models for images are something like DALI or Midjourney or Sora, where you can give it a text prompt and it generate an image for you. So it understands how terrestrial objects look like, or SAM or segment anything model. So we are starting to develop models of that kind using time series. So if you use time series on ZTF and learn from that, you should be able to use it on another service. There are many foundation models of time series also, but most of those are in the commercial domain. I don't know whether I've been telling you to go to the next one. Let's go to the next one, please. Yes, here. So foundation models for time series we have been using, and most of these though use regular time series. For instance, consider stock market. If it is not a holiday, the stock market always opens at a specific time, next year at a specific time. So you have values at that time. And then it's somewhat easier to analyze this time series. But with astronomy, with the irregular gaps, it's harder, but we have been developing things related to that as well. Next, please. And this is where the power of archives comes into picture, the main topic. So with DPOS, the digitized Palomar Observatory Sky Survey, or ZPIT that we've been working on, all the data is public. This provides variability information over several decades. So the DPOS was more than 25 years ago, ZTF is continuing. You can get really large compared to our lifetimes, because our lifetimes are a few decades. Compared to that, 25 is large enough. But the lifetimes of the stars are millions of years, of course. So a particular star, you cannot find it being born and then aging and dying. But when you look at 1 billion stars, then there will always be a few stars that are being born, few stars that are at an intermediate age, and few stars that are dying. So that is how statistically you can understand that. And so we have better ability to internalize these archives and so on. So again, the URL is there for you to take a look at and get those data, etc. There are more surveys coming in, like Roman and Rubin's. And then what we have also been looking at are anomalies, because you understand what known classes are, but once you know what the classes are, there are always, through these gaps, you're going to find interesting objects. And these anomalies are like tips of icebergs. So it's difficult that there'll be only one of a kind in the universe. But once you find one of a kind, that tells you that how to find more of those, and then you can look for that entire iceberg. So that is another thing that we are doing here. So finally, I come to ZAR, the game that I told you about. This is the QR code that is here. So if you have your cell phones, maybe you want to take a photo of that. That will take you to the URL from which you can download the game and play it. So what this allows you to do is be able to catch the transients that are there. And in fact, I have a few cards that I will leave here. Those also have some of these URLs, information about the game. You can pick some of those later on. So what happens here is that when you load the game, you can see the sky. And you can see, in fact, the same part of the sky where you are pointing the phone to. And with iPhones, you may need to slide it. With Androids, you can move the sky, move the phone around and be able to see that. It's loading right now on my phone here. And you can see that as I move it along, you see different things on that. And on that are some of these objects, the hosted objects, orphan objects, nuclear objects, variables, etc. And then you can point when you see one of those, you can touch it, then it will bring up the time series for that object and you'll be able to catch it. Let's go to the next slide, please. So the idea came to me from Pokemon, and that's why I was telling you that it has an analogy of Pokemon. Pokemon are of different kinds. Similarly, variables and transients are of different kinds. I thought that why not have these different families and let students learn about astronomy through this game. And so, next slide, please. So we have got these hosted objects, which is objects that are in a galaxy, or nuclear objects where objects that are in the galaxy but close to the center of the galaxy, orphan objects where there is no associated galaxy or variable which is going up and down. And then there are two exciting types, wild type 1 and wild type 2. This is of most interest to us because this is where our classifiers have failed in some way. So more than one classifier tried to claim that object. So classifier 1 says, this object is my type. Classifier 2 says, this object is my type. And both cannot be right because those were different kinds of classifiers. So this is where ambiguities come in because incomplete data that we have. And that is where our neural networks, human neural networks can be much better. So by humans looking at these data, we may be able to learn from you as to what is the real type. And that will help us improve our classification algorithms also. So right now, this is not a citizen science project. We have no way of getting the data back from you, but you can still form teams, try to start discussions around that, and also introduce it into classrooms so it can be a STEM activity. Each week, learning about different kinds of objects. So again, there are leaderboards there are internal games, there are history inside the game, so you can learn about different kinds of things. And so these are a couple of screenshots that we have for the game that you can look at. So these are some leaderboards that are there, and you can earn badges. So for each type of object, you can get badges as you get more and more objects of that type. You have a question? How does it? So what we have is that for each of these objects, what you can see here on the top right. So sorry, we should let's go back one more. Yeah, here. Yeah. So in the bottom right corner, what you see is a time series. This is one object that is there. On the x-axis is time, on the y-axis is the brightness. So for each object, you are going to be able to see how the object was changing. There is some metadata about that. There are some numbers there, the position RA day. It has a certain cost to catch. What is its magnitude? What is its rarity? And the number of points that you get is based on the physical properties of the object. So you start learning about which properties are more interesting to astronomers. So there's one number there called TNS0. So the TNS is the transient naming server, and it notes something like how many spectra were taken by astronomers. So if astronomers take spectra, which are expensive to take, that means that astronomers are very interested in that. And so what that means is that starts telling you as to which objects are likely to be more interesting, more rare, etc. And you get to understand what different kinds of objects look like. So if you were to follow it up in small telescope, not really small, but intermediate size, you may be able to do that, try to get it right. Okay, next slide, please. So this is where the leaderboards are, yeah, and that's where we had the weekly leaderboards, and then the next one, yeah, this is where the badges are. You can get different kinds of badges as you start advancing in the games. So what I'm going to do is that I'll end in 2 more slides and then we can leave time for questions later on, more discussion, because you may have specific things about different archives, etc. But local collaborations are possible, competitions are possible. You can learn from the different lighters that are there. You can reason about ambiguous sources, and that is where we would like to learn from different humans as well, how things progress. And of course, share and just add how you can do more things. So this is the summary of my talk. Astronomy archives are very underexplored because astronomers have been going after the low-hanging fruit and publishing papers, but there are more papers to be published in archival data that are there. And astronomers are happy to collaborate with teachers and with students on projects, etc. So we'd be more than happy to do that. And statistical and traditional machine learning is still used very extensively in astronomical time series, but there's scope to do more. Modern ML methods are being used more and more. And in all of this, explainability and interpretability is very crucial. So when you do something, you should try to reason how that is happening. And I'll stop with that, and then we can take questions or go to the next part of the program. And some of you should take these and try to spread the word about it. Thank you.
We now open the floor for an interactive session. Please feel free to speak questions and engage with our speaker. Okay. Thank you so much, sir. Now I call upon to our honorable Dr. Sir, to come forward and guide us on this.